Hello George and Lars, welcome to my very brief video describing my 45 filters for this last image processing Handin. I made 45 filters and here you can see a crossed off the ones I made, so all the point processing except for pastels and a bunch of the neighborhood aberrations, all the morphology, all the blob analysis, and a couple of the geometric transformation filters. So I'm just gonna give a brief run through of most of the filters. 45 is a lot, so I'm just gonna really quickly go through so you can see that they work, and I'll try to keep it as short as possible. So yeah. So here you can see the first filter, the invert filter, the brightness filter, the contrast filter, the grayscale filter, the gamma map filter, currently with a value of 0.45. The alpha blend filter, currently blending a beautiful picture of Lars. The threshold filter with a threshold value of 80. A hue shift filter. A sepia filter. And the color depth filter, currently simulating a color depth of 4 bits. So that was just a couple of the point processing filters. Let's just move on to some of the neighborhood filters. First we have our standard mean blur, this time with a radius of 3. Here it is with a radius of 7. Changing it was simple, just basically changing a single parameter here from 3 to 7. So not the difficult. Here we have a mean blur. It's much nicer. I mean a median blur, much nicer than the mean one. And here we have a Gaussian blur. This is a 3 by 3 mean blur using a disk. And the same disk mean blur, but this time a 7 by 7. Here we have a Sobel edge filter with a kernel width of 3, that means a radius of 1. It's more edge detection, this time with a Pruitt kernel. To include neighborhood processing, we have an emboss filter. Moving on to morphology, this is a 3 by 3 erosion. You can see the original binary image over here. This is the eroded one. And here it is dilated again. Moving on to compound aberrations. This is the image opened up using a 3 by 3 or a kernel with a radius of 3. And here we have it closed, also with a radius of 3. And here we see some boundary detection. Works well. It works kind of well. Okay, moving on to blob analysis. So for blob analysis, I'm tracking the color blue, and you can see here that it's tracking a single blob here that it colors green in our case, and this is the bounding box around it, and the white circle is the center of mass, and the red circle is the center of the bounding box. Meanwhile, we have a couple of values here that are just printed out. We have, hopefully you can see it, we have the centroid position here, which is the white circle, and this is the bounding box ratio, the blob area, the perimeter, the circularity, and the compactness here. So hopefully you can see these values. Yeah, so blob analysis definitely works. Moving on to geometric transformations, this is a crop filter, currently from 1010 to 200 100. Here's the image rotated 90 degrees counterclockwise. The rotation algorithm in this case only works in steps of 90 degrees. Here the image is scaled with a value of 1.5 from the upper left corner. Finally, we have a tile, which in this case is implemented mainly as a kind of offset function. So In this case, it's offset negatively, so around 100 each direction. Okay, so let me go a bit in depth with just a couple of the filters. Let's start with the point processing filter. I'll just take this color depth filter. Basically what it does is that it takes a color of an 8-bit channel, which means a 24-bit image, and it reduces the bit depth to a value specified here as a function argument. So in our case, when I use this function, I choose 4. So the way it does this is that it simulates this lack of discreteness, if you can say that. It has fewer steps because it has fewer bits. So it calculates the new max value here using just by taking 2 to the power of the new bit depth and minusing 1, and calculates the current ratio of the current value of this particular channel. So takes the channel, divides it by 255, and then this ratio is multiplied by the new maximum, and finally it's multiplied by 255 divided by the new maximum to get it back up to the range of 0 to 255. This procedure effectively has the effect that we have a significantly smaller amount of colors to choose from, because the steps are simply reduced, so we lose detail, and that makes it look like the bit depth is reduced as well. So let's move on to a neighborhood filter. So this is the mean disk blur. It says a 7x7, but it can actually take any kind of radius. So with a radius of 3, it would obviously be 7x7, but any kind of radius can go, because we take it as a function parameter argument. So basically what it does, it creates, it does standard stuff like border checking, and then we have a int array here basically that's calculated based on the size of the radius, and this kernel is filled up with values of 1 if it is inside the radius of the circle, or 0 if it is outside. So this is done using basic, it's like vector math basically. Well, it is vector math. So this little piece of code does that. After that, we simply calculate the new kernel values here, and then we loop through each pixel surrounding our the pixel in focus, depending again on the radius here, and we just multiply that value with the kernel value, which is either 0 or 1 in this case. So this gives us like a disk effect instead of a box effect. And finally, we normalize the kernel value, so this is just what happens here. In the end, we make sure to delete this array, because we made it on the heap, so we have to delete it. Let's move on to a morphology filter then. So here's my erosion filter, and what it basically does is it takes a pixel and then it checks the pixels around it, and it works on a binary image. So the idea is that it has a kernel made out of ones, and it checks a certain pixel and then pixels around it based on the kernel radius. And if any of those pixels outside that pixel are not 1, it sets that pixel to 0, so it has an effect of eroding all the pixels that are not surrounded by a bunch of other white pixels. So any white pixel that's kind of alone or just some kind of appendage will be deleted and replaced by just black pixels. So it's pretty basic, because it's like a standard kernel loop here. We loop it through based on the radius of the kernel, calculate new indexes, and this is basically the place where stuff happens. If the input pixel around the kernel, we make a logical AND, and if it's not 1, then that means that we found just 1 pixel somewhere in the vicinity that is not 1. So we put the pixel of our focus to 0, and we remember to delete our kernel and just return because we already did our work. So that's about it for the erode function. With regards to the grass fire algorithm, I implemented this using a struct, so it's located in here, and it's just called grass fire. And well, it works pretty much like any other grass fire algorithm. We have an input image, output image, they're binary of course, and other stuff like width and height necessary. And we have this little label thing that increases every time we find a new blob. So what it does is use a grass fire algorithm to scan a binary image for blobs. So we start the fire here. We start with a label of 1, so we can distinguish it from all the zeros. And we just loop through the entire array of pixels here using a x and y double for loop. Calculate the index, of course. If we find a pixel that is 1, we start the fire. You can see we call the fire function here with parameters x and y, and we also increase the label so we're ready for our next blob. So the fire algorithm here works recursively. Basically, first it just does sanity checks to check that it's not going to go outside the boundary, because if it is, we just return. Otherwise, we calculate a current index, and if the stuff that we're trying to set fire to is 0, we just return as well. On the other hand, if it is 1, we set it to 0, so we burn it, and we set the output at this index to be the label, so we can keep track of basically we say we found a blob here. So, and then we just do grass fire on all the 4 near well, the 4 surrounding pixels. So that will be x and y minus 1. Here you can see that I do it on all 4 times. So. And this recursive algorithm basically just does our job. It also has a simple function just to convert the blob information to image data, so we can display it just primarily for debugging purposes. So the blobs that are found by the grass fire algorithm, they're analyzed by this simple function here called analyze blob, and it just receives blob data to analyze on, and it returns a struct of type blob here, which is a very simple little struct I made here. It just has information about centroid, it has a bounding box area, the label it has, and information about the perimeter, and methods to get the degree of circularity and compactness here. And the analyze blob basically just checks blob data for a blob of a certain label, and then it extracts all this data using, well, several different techniques. Yeah, I'm running out of time, so I won't be covering them in detail. So let's just quickly move on to geometric transformations, which is the last thing we'll be covering today. So with regards to geometric transformations, I'll be covering my tile function here, which is actually more like an offset function, but never mind that. What it does is take an image and offset it a certain amount of pixels, and any pixel that is outside our border just gets looped out to the other side of the border, so it wraps around basically. So how it does this is just well, a standard for loop through all of the pixel. It has an x and y offset, and it just basically just adds this offset to our x and y values. Then it checks if it's above or below, it's above width or height or below 0, and in these cases it just corrects it so it gets on the other side, so it wraps around. And then it calculates a new out value using these new x and y values, and then it sets this new out index here to the previous index, so we get the tile effect. So I'm running out of time now, so this is about it. Thanks for watching this short video on all these 45 filters. Bye bye.